I hope you are having an amazing day. Welcome to today's presentation. As you can see on the screen, our topic today is Mohrs circle. In this presentation, we will get introduced to Mohrs circle for plane stress, its construction, and the important results that can be deduced from it. Before delving into Mohrs circle, we will briefly review the state of stress at a point in three-dimensional Cartesian coordinates, plane stress conditions and stress transformation for plane stress conditions. Mohrs circle is a geometric representation of the two-dimensional transformation of stresses. Mohrs circle is commonly used by engineers to graphically analyze the principal and maximum shear stresses, as well as to determine the inclination of these planes. Okay. Let us straight away begin this lecture session. The most general state of stress at a given point can be represented by 6 stress components exerted on the face of a cubical element in Cartesian coordinates. Now we all know that a plane can be defined by its normal. For example, xy plane has its normal along z-axis. In other words, z-plane is the one which has normal to xy plane. Similarly, yz plane has its normal along x-axis. In other words, x-plane is the one which has normal to yz plane. Zx plane has its normal along y-axis. In other words, y-plane is the one which has normal to zx plane. Putting in simpler terms, x-plane has normal in the x direction, y-plane has normal in the y direction, and so on. Right. The 6 components of stress are illustrated in the figure. In x-plane, we have sigma xx, tau xy, and tau xz. Similarly, in y-plane, we have tau yx, sigma yy, and tau yz. And in z-plane we have tau zx, tau zy, and tau zz. 3 of these components, sigma xx, sigma yy, and sigma zz, are the normal stresses exerted with the same orientation as the coordinate axes. The remaining ones are the components of the shearing stresses on this element. But obviously these components in total count to 9 instead of 6. But due to the equality of cross-shear, sigma xy is equal to sigma yx, similarly sigma yz is equal to sigma zy, and sigma zx is equal to sigma xc. Therefore, state of a stress at a point in a three-dimensional space can be represented by 6 components, 3 normal stress and 3 shear stresses. Since normal stresses are quite evident, for simplicity, we replace sigma xx with sigma x, sigma yy with sigma y, and sigma zz with sigma z. Okay. Now we will try to understand about the plane stress conditions. Plane stress conditions are also known as biaxial stress conditions. This usually occurs when 2 parallel faces of the cubic element are free of any stress, as in the case of thin plates. Consider the lamina as illustrated in the figure. The parallel faces free of stress are perpendicular to the z-axis, then the stress components sigma z, tau zx, and tau zy vanishes, and what is left behind is sigma x, sigma y, and tau xy. Obviously tau yx is equal to tau xy. Plane stress conditions also exist on the free surface of a structural element or machine component where any point of the surface is not subjected to an external force. In the cylindrical structural component, free cylindrical surface is under plane stress conditions since no external force is acting on it. Equations for normal and shear stresses acting on an arbitrary plane inclined to the plane with known stress can be deduced in algebraic form from first principles. Such expressions are called stress transformation equations. The figure shows two-dimensional state of stress. The stresses are acting on the faces perpendicular to the plane of paper. Sigma x, sigma y, tau xy, and tau yx are known values of stress components. We are interested in estimating the stresses on an arbitrary plane that is inclined to the known one by theta degrees as shown in the figure. It is to be noted that an infinite such planes are possible. From first principles we can derive the stress transformation equations as given below. The normal stresses acting on the new plane is given by sigma x1 equals sigma x plus sigma y divided by 2 plus sigma x sigma y divided by 2 cosine 2 theta plus tau xy sine 2 theta. The shear stress acting on the plane is given by tau x1 y1 equals minus of sigma x minus sigma y divided by 2 sine 2 theta plus tau xy cosine 2 theta. Now we try to understand how Mohrs circle can be geometrically constructed from the stress transformation equations we have already seen. The stress transformation equations have been reproduced here. Now rearranging the equations we can write. Sigma x1 minus sigma x plus sigma y divided by 2 is equal to sigma x minus sigma y divided by 2 cosine 2 theta plus tau xy sine 2 theta. Now squaring and adding the two equations, theta can be eliminated. The resulting expression is sigma x1 minus sigma x plus sigma y divided by 2 whole squared plus tau x1 y1 squared equals sigma x minus sigma y divided by 2 whole squared plus tau xy squared. A closer examination reveals that this equation is similar to the equation of circle with radius r and center at the coordinates h, k, which is expressed by x minus h whole squared plus y minus k whole squared equals r squared. The origin hk corresponds to sigma x plus sigma y divided by 2 and 0 respectively. The radius of the circle is root of sigma x minus sigma y divided by 2 whole squared plus tau xy squared. In other words, the stress transformation equations can be geometrically represented by a circle. X-axis, as you can see, is tensile stress and y-axis is shear stress in the Mohrs circle. Here important point to remember is that angles in Mohrs circle are twice the orientation angles for the planes. Locate the center of the circle. Center lies on x-axis, that is sigma axis, at coordinates sigma x plus sigma y divided by 2, 0. Radius r, as we have seen, is root of sigma x minus sigma y divided by 2 whole squared plus tau xy squared. With these data, the Mohrs circle can be constructed. Sign convention needs to be followed for the construction. Tensile stresses are taken as positive and compressive stresses as negative. When the shear stress on the opposite faces of an element result in a clockwise couples, then shear stresses are taken as positive and vice versa. Here the shear stress and the x-planes produce a counterclockwise couple and therefore taken as negative, as depicted as point A. The conjugate point B experience shear stresses which produces clockwise couple and therefore taken as positive. Point A corresponds to stress in the x-plane, that is sigma x tau xy, and point B corresponds to the stress in the y-plane, that is sigma y tau yx. Tau yx is equal to tau xy and has been replaced for simplicity. Now we are interested to estimate the stresses on an arbitrary plane that is inclined to the x-plane by theta degrees. The corresponding stress states are denoted by a dash and b dash on the Mohrs circle, a dash for x dash plane and b dash for y dash plane. A dash and b dash are located by measuring 2 theta. To locate the point, we follow the same sense of rotation as the arbitrary plane. Principal planes are planes which do not have any shear stress component. Now we will locate the principal planes and principal stresses in the Mohrs circle. This is the stress transformation equation for shear stress. Equating the shear stress component in the stress transformation equation to 0, we observe that tan 2 theta is equal to tau xy whole divided by sigma x minus sigma y divided by 2. In the Mohrs circle, principal planes are denoted by the diametral points located on the x-axis. That is A1 and B1 in the figure. We can estimate tan 2 theta p. This distance is half of sigma x minus sigma y, therefore tan 2 theta p is equal to tau xy whole divided by sigma x minus sigma y divided by 2, which corroborates the previous result. By convention, principal planes are denoted as sigma 1 and sigma 2. The center of the Mohrs circle is at sigma x plus sigma y divided by 2. Accordingly, principal stresses are this distance plus or minus the radius. Radius is given by root of sigma x minus sigma y divided by 2 squared plus tau xy squared. From the figure, we can observe that the principal planes corresponding to sigma 1 and sigma 2 are mutually oriented by 2 theta equals 180 degrees. This implies that principal planes are at right angle to each other. The largest shear stress corresponds to points D and E. The numerical value of this is in fact the radius of the circle, that is root of sigma x minus sigma y divided by 2 squared plus tau xy squared. Diameter of the Mohrs circle is given by the length A1b1, that is sigma 1 minus sigma 2. Therefore max shear stress is also equal to sigma 1 minus sigma 2 divided by 2. Now we determine the normal stress in the plane which experienced the largest shear stress. This is nothing but the x-coordinate of the points, that is sigma x plus sigma y divided by 2. This is also equal to sigma 1 plus sigma 2 divided by 2. If shear stresses are absent and identical direct stresses, biaxial tension/compression, are acting in two mutually perpendicular directions, the conjugate points A and B coincide with the x-axis, that is A1 and B1, then sigma 1 equals sigma 2 and the Mohrs circle shrinks or degenerates into a point, sigma x equals sigma y equals tau x y equals 0, and no shear stresses at all develop in any of the xy planes. We know that the center of the Mohrs circle lies at sigma x plus sigma y divided by 2 on the sigma axis. If sigma x plus sigma y equals 0, then the center of Mohrs circle coincides with the origin of the sigma tau coordinates, and the condition known as state of pure shear exists. The angle between principal planes A1 B1 and max shear planes is 2 theta 90 degrees. Another important result you can infer is that the planes of maximum shear stress occur at 45 degrees to the principal planes. The metals and alloys are weaker in shear and the shear strength is just half of the yield strength. One practical observation in which you can correlate this is the tension test of ductile materials. It has been established that ductile materials exhibit a characteristic cup and cone fracture under tension. This is illustrated in the figure. The planes of maximum shear stress occur at a 45 degrees angle to the principal planes, and this accounts for the characteristic cup and cone fracture appearance due to failure due to shearing along these angled planes. I shall wind up the presentation here. Thank you for your attention. I welcome your comments. If you liked the video, kindly like it, share it, and most importantly subscribe to my channel. Also enable the bell icon for the notification for new videos. Have a great day, thank you and bye-bye.